Okay, thank you. It's a pleasure to be here again. It's always nice to give a talk in my alma mater, though the place has changed so much that it's hardly recognizable. Anyway, I'm going to be talking about some particular questions to do with what happens to the state after quantum quench. There have been quite a lot of talks already about what a quantum quench is, so hopefully I don't need to actually describe it. I'm going to be talking about a quantum quench from an initial state which has area law entanglement and short-range correlations. And I'm in particular going to be considering models in which the system thermalizes exactly. So even though these are going to be integrable models, exactly solvable models, I'm going to start from a particular state where I know the system goes to a Krebs state. So that's either a good thing from one point of view, or maybe you think it's a bad thing in that I'm not considering the most general case. But this is in a mathematics institute, so I think I'm allowed to do anything as long as it's mathematically interesting. Okay? The questions that I'm going to try to answer is, if we take first of all, to do with revivals. If we take a finite system, now a large but finite system of linear size L, what is the behavior of the overlap between the state at time t and the initial state? So initially we expect this to decay quite rapidly as a function of time, but the question is, are there revivals at times roughly of order L, because we have this idea that there's going to be ballistic propagation and therefore at times of order L one might expect to actually see a revival of the initial state. The other kind of question that I want to ask is, how does the entanglement entropy between different bits of the system increase with T before it saturates at its thermal value, which is obviously going to be a volume law rather than an area law. And I'm going to answer these in conformal field theories, and both in two-dimensional conformal field theories, but I'm particularly interested nowadays in what happens for dimensions larger than 2. And the reason for looking at CFTs is that they are analytically tractable. They do describe the long distance low energy physics. However, applying CFTs then to the quench scenario where you're populating the high energy states, then it's just a model, okay? So it's a model which is interesting because it's solvable, but then you should really ask the question, what happens if you change the theory slightly? And this is something that I've been interested in, but I'm not going to address here. So if you change the theory slightly, so it's not exactly a conformal field theory, then interesting things happen, but I'm not going to actually discuss this here. So, and most of the results that I'll discuss for 2 dimensions, that's 1 plus 1 dimensions, are going to be true for generic CFTs, but for d larger than 2, we have results only for free Gaussian theories, which are kind of special in a way, but we usually think of free field theories as being trivial, but from their entanglement point, their entanglement properties are by no means trivial. And that's what I'll be talking about. Or holographic theories, and And there I will borrow some results from our friends across the way there in high energy physics, where there's a great deal of interest in this through the ADS CFT correspondence, though I won't discuss that explicitly. Okay, so this special initial state that I'm going to take is the one that Pasquale and I did in our 2005 paper, where we take what's called a conformally invariant state, which is basically a state with basically the continuum limit of a product state. Okay, you can think about it this way, and we smear it slightly. That is, we evolve in imaginary time with the conformal field theory Hamiltonian. So this, we actually chose this state because we could actually do the calculations, and we then found that at least in 2 dimensions, and I'll also show you that for free field theories in D larger than 2, this goes that subsystems exactly thermalize. And so although this is a special state, as I said, A, it's one that we can actually do calculations with, and B, it does thermalize. So you can think of this as a model for maybe a non-integrable system, which we would also expect to thermalize and not go to a GGE. So let me start off by talking about revivals, and in 2 dimensions. I'll begin with. So we're interested in the overlap between the state at time t, which is the time evolved initial state, which is this, and the product and the scalar product of this with the initial state, which is this. And now you can immediately see why it was useful to actually consider this particular state here, because what you're really doing here is evolving the state B for a total imaginary time beta over 2 plus IT. Okay, and so if you think about the path integral for this, where space runs around this circle, so space is going to be a circle, and imaginary time runs up here. This expression here is basically the partition function for the conformal field theory on this annulus, with boundary conditions on the upper and lower edges corresponding to this conformal state B. And we have to normalize it in this particular way. So let me first talk about the initial case. So what we're always going to assume is that L is much bigger than beta over 2, or beta. And if T is also small, then L is going to be much bigger than T as well. So basically this annulus is very long and squat, okay? So from that point of view, we can think of the partition function, or the logarithm of the partition function, as being the free energy of a 2-dimensional classical system between 2 parallel plates. One plate here, one plate here, okay? And then the free energy is going to be dominated by the Casimir energy between these 2 plates. And for a 2-dimensional conformal field theory, we know this goes like pi times the central charge, the length around the system, divided by the width. And and it has to be proportional to L because L is much bigger than W, so the log of Z must be extensive in L, and it must also be dimensionless. So it must behave like this, and the only thing that you also need to know is that the coefficient of the Casimir energy is pi c over 24, where c is the central charge. So if you plug that expression in there with L being L and W being beta over 2 plus IT, and you normalize it properly, this is what you get. You subtract these two, and what you find is that the overlap decays initially as a Gaussian, not exponentially, as you might expect. The phase decays like e to the IT, but you have to take the modulus. And it also then, if you take large t, or we need to actually discuss how large you are allowed to actually take t, but if you literally take large t in this formula, you can see this thing goes to a constant, and the constant is in fact just 1 over the square root of the density of states. It's actually the density of 0 momentum states, because you started from a translationally invariant state, so you can only ever get translationally invariant states there. And what this basically says is that at large times, the state of the system becomes a typical state of that particular energy, okay? So that the overlap between that and the initial state is just basically 1 over the possible number of states. If you check where this is actually valid, so what has to happen is that the corrections to this, which you also know are small, then you find it's actually valid for a generic CFT, that is with some fixed value of the central charge t in this particular region. So large enough t, but still going like the square root of L. Now actually this particular result you can easily in fact see is just basically due to interference between the high energy states. So if I take this expression, I plug in a complete set of intermediate states here, the energies of a conformal field theory in a system of finite size L go like 2 pi delta over L, where delta are the allowed scaling dimensions of the area. So basically it's going to go like this times the density of states. It's not quite the density of states because there are matrix elements involved too between the state and between the energy eigenstate and the initial state. But it's some function of delta. And it's well known that in fact this density of states, or this slightly modified density of states, for large delta and fixed c behaves like this. And so if you plug this into here and you do a steepest descent calculation, which turns out to be valid when L over this thing is large, okay, then you get back to the result that I just showed you.
John, what happens if delta is less than c? Is that the imaginary density of states?
Well, it can't be. Okay, that's very interesting. Okay, so I'm about to actually tell you what happens there. So, in a rational conformal field theory, this does not happen. Okay.
Zero.
The zero doesn't count there. Okay. Well, what happens is that the saddle point occurs at large delta. So let's this is supposed to be true at fixed C and large delta. Okay, so at fixed C and large delta, I can ignore this term. However, I'm about to tell you something, which is it's now known that in a holographic conformal field theory, which is a CFT with large C but a low lying density of states for small delta, then most of the deltas are in fact of order C, and they're even bigger than C over 12. So this formula for a holographic CFT is supposed to be true for large C when delta is of order C but bigger than C over 12, okay? And if you then plug this back into here, you can then do a calculation not where the large parameter is L over beta plus IT, but where the large parameter is C. And it's a slightly different, I mean, it gives the same answer, but its range of validity is much bigger. And you then find in a holographic CFT that this form that I showed, this decay to the plateau value, is true for 4 times all the way up to actually C times L. And this is understood within ADS CFT by the fact that when you do this quantum quench on the boundary of the ADS space, you introduce energy in, it collapses in, it forms a black hole. And the thermalization of the theory is the Hawking radiation, essentially, from the black hole. And of course, the black hole doesn't then dethermalize or anything as far as we know. So basically what happens is that in a holographic CFT, basically the system thermalizes and that's it, basically. Nothing else interesting happens up to a time of order C times L, which is huge, which is a sort of Poincare recurrence or something that I don't quite understand anyway. Okay, any questions about that so far? Right.
So, question actually, but I might as well ask. So you said the settle point occurs. So you had L divided by beta over 2 plus IT was large. So maybe it would be the other way around, no?
L. So this is beta over 2. This is beta over L, and the saddle point when you work it out is for L over beta large. Okay, you can do the calculation and actually check it. Okay, so the opposite case of a holographic theory is a theory with small c, and these are the rational conformal field theories. And then in that case, we expect to get revivals because the allowed values of delta are then rational numbers, basically. So if you now insert a complete set of states into here, because delta is rational, we expect to get revivals at t is an integer, well, maybe partial revivals at integer times L over t, and then complete revivals at q times that, where q is the smallest common denominator of all these rational numbers. So that's in fact what we do in fact find, and I'll show you some explicit results in a moment, but this can all be understood easily within this quasi-particle picture that Pasquale and others explained. Basically, if this is time, this is space, we view the initial state as a source of EPR pairs propagating in opposite directions around the system, and you can see then if we have periodic boundary conditions after a time L/2, the particles meet again, and the idea is because it's an integrable system, they sort of carry all the correct phase information so that when they meet again, they exactly reconstitute the initial state. Now, in the example that I'll show you, that actually doesn't quite happen, and I'll explain why. Anyway, in fact, we know a lot more about the partition function on an annulus. So if we write Q is this thing here, which is a kind of modular parameter of the annulus, then that expansion in terms of intermediate states can be written as a sum over powers of Q, where these are basically the allowed scaling dimensions. Delta comes from some finite set for a rational conformal field theory. So this is basically a sum over this finite set of rational deltas, and then the sum over n over these integers n gives what's called a character of whatever the infinite dimensional algebra it is underlying this rational conformal field theory. And for all kinds of cheap reasons, these characters actually form a linear representation of the modular group. So the modular group, if we write Q is e to the 2 pi I tau, is generated by tau goes to tau plus 1, which is basically the same as t goes to t plus L over 2. There's revival time, so that's not so unexpected. What is perhaps unexpected is that there's also they transform linearly under tau goes to -1 over tau, and basically that's basically t goes to L squared over t. So we get all these revivals at integer multiples of L over 2, but then we take inverses of these and we get rational values of t which are smaller than L2. Okay, so we get incomplete revivals there also. In fact, if you know a little bit about the modular group, this is the classic picture that you will see in any textbook about the modular group. So this is the upper half tau plane, and this thing is called the principal region here, and then the action of the modular group is to either move this to the right or left, or invert it to get something like this, which can then be moved to the right or the left, or inverted again to get this. And you get this incredibly complicated structure, which near the real axis condenses on every rational value of tau, or t over L, basically. So basically the behavior up here, which is the initial behavior, can be mapped into the behavior in any one of these triangular domains here.
John,
So, yeah.
what is the weight of the modular form?
Well, it's not a they're not. They form a finite dimensional representation of the modular group.
So,
Okay, so they're not a modular form. Yeah. Okay, so what basically happens, because tau was this, so beta over L is small, so as we increase t, we basically move along a path here, right? and we move through an infinite number of these domains. And as we decrease beta over L, we just move through more and more of them, and we see more and more structure. So here's, for example, is a result for the Ising CFT, where we're doing a quench from above the critical point to the critical point. And this is the logarithm of the overlap, basically. So what you can see is this very fast initial decay, which is a Gaussian but hardly looks like it. And then to this plateau value here, but then on top of this plateau there's all kinds of structure. And you expected to get the first complete revival at 2t over L equals 1, but in fact you actually get destructive interference there, and that's because there are two types of quasi-particle here, and they destructively interfere because the scaling dimension of the energy operator is 1/2, basically. Okay, and then as you decrease beta over L, you see more and more structure here. Okay, so all of this can be understood just from the point of view of the modular group, but you would expect to actually see this for any rational conformal field theory. Now, I do want to point out that although we actually have these peaks, these are on a logarithmic scale, and if you don't take the logarithm, they're exponentially small with the size of the system L. So you have to take a finite system to really have a hope of actually seeing this. Okay, so now I'm going to talk about revivals for d bigger than 2, where, as I told you, you either do holography, where I claimed you don't get revivals, or I looked at a free field theory. So now we have a d-1 dimensional space, one time. We can look at it on some finite d-1 dimensional space, and you could think about doing it on the torus, for example, and then it sort of depends whether the torus is rational or not, whether the cycles around the torus have a rational ratio. That's kind of complicated. It's more natural, although perhaps even less experimentally relevant, to actually look at it on a sphere. So space is going to be a d-1 dimensional sphere of radius r, and we have time. So the nice thing about this is that if we have the Hamiltonian of a CFT on a sphere, then we can still make this logarithmic conformal mapping, where we see that the eigenvalues of the Hamiltonian are in fact the eigenvalues of the dilatation operator in RD. So there's still the scaling dimensions of the theory. Okay, so what we want to do, so the eigenvalues are the eigenvalues of the Hamiltonian on the sphere are in fact delta over r, quantized in units of 1 over r, and so forth. Okay, so we want to compute as before. It's just the same calculation. We are still going to start from this CC state, this rather special state. So we are going to want to compute the partition function on something which is a sphere cross a line interval. Okay, so just imagine that, because I can't draw it very well. Okay. And once again, this is going to be expressible as a sum of powers of q to all the possible scaling dimensions, where now the modular parameter is this, where w is beta over 2 plus it. And once again, we can make exactly the same argument as before. If we're interested in small times and large r, then we basically have a sphere, a kind of spherical shell, which is very, very thin. And once again, it's dominated by the Casimir energy. So the log of z is going to go like sigma, which is basically the Stefan Boltzmann constant of the theory, but we don't need to get into that, times the area of, or the volume of this space of the sphere, and because it has to be dimensionless, the Casimir energy now has to go like 1 over the width of this shell to the power d minus 1. So if we plug this in here, we get basically a very similar formula, a little bit more complicated, but basically what you see is that for small t, you expand this out, this thing becomes linear in t, but that's it, and so that's just a phase. The next term is t squared, and so if you take the modulus here, you get a Gaussian decay once again to a plateau value. So this is true. This is going to be true in a generic CFT. Once again, if it's holographic, you expect this to persist up to late times where this is basically, this sigma here is going to be large. Okay. Now a free field theory. Okay, so to do the same calculation in a free field theory is an interesting little exercise, which I won't go through for you. I'll just tell you the answer. So the action of the free field theory on a sphere. So it's a massless free field theory, but when you put it on a curved space, you can always couple to the scalar curvature, which is r to the minus 2, where r is the radius of the sphere times a parameter which is usually called psi. And in that case, there's a nice formula in terms of Q, and it looks like these kind of formulae that you get in two dimensions. You can see this. We have Q to the energy, and the energy is the square root of, this is the Laplacian basically, plus psi, because psi enters there. So these are the eigenvalues of the Laplacian on a d minus 1 dimensional sphere. You might recognize L into L plus 1, which is what you all learn in as an undergraduate in quantum mechanics for d equals 3. That's okay. So and then what comes in here is the dimension of this particular angular momentum representation, which is the d-dimensional analog of the 2L plus 1 that you learn about. Okay. So in 3 dimensions, this would just be 2L plus 1. Okay, so that's a nice formula, but you see it's a complete mess because of this square root, right? So these aren't Q2 integers by any means, but the amazing thing is that there's a special value of psi which is called a conformally coupled scalar field, and it's non-zero. And if you put in that value as a function of d, this thing becomes a complete square, and you get q to either an integer or a half integer. And then, because it's q to an integer, you get, just for the same reason as before, you actually get complete revivals. So if you have a conformally coupled scalar field on the surface of the Earth, right? If seismic waves were a conformally coupled massless scalar field, if there were an earthquake here, no, in California, sorry, and you wait a time of the order of the radius of the Earth, then this earthquake would exactly revive. So we hope that earthquakes are not described by a conformally coupled scalar field. Okay. Now the interesting thing is, this is a kind of generalization of the two-dimensional result, which, as you may know for a scalar field, is the generating function for the number of partitions of an integer. And for d equals 4, this is a bit more simple, and it's actually the generating function for what are called plane partitions. And that's been kind of studied mathematically quite a lot. But the interesting thing is that this also has, as well as transforming simply under tau goes to tau plus 1, also transforms under tau goes to minus 1 over tau. So once again, in this free field theory on the sphere, you actually get structure at rational, all rational values, and you get a similar kind of graph to what I just showed. So this is kind of recreational mathematics, okay, and whether it has anything to do with physics, I don't know, but it's fun anyway. So now I want to talk about entanglement propagation. Yeah.
Was it already known that about the specific value of C being the normal field theory?
Of C. Well.
Was it already known that it's conformally invariant to that special C?
Yes. That's why it's called conformally coupled, because then the action is conformally invariant. Yeah. Otherwise, it's not. Yeah.
Excuse me. Yeah. So what was the method in the previous transformance? The method.
The method of how I calculated.
No, the metric. Square root of G. What did you?
That's the metric on the sphere. You know, it's the usual. You can write it in spherical polars, and it's the usual thing. Okay. So it's just the standard metric if you embedded the sphere in a Euclidean space. Okay. Yeah. Excuse me. Yeah, I didn't explain that. Okay, so now I want to talk about entanglement. So this is just a definition of entanglement. I don't need to actually talk about that, but now we want to discuss entanglement after a quantum quench. And the idea is that because this system thermalizes, or a subsystem of linear size A thermalizes after a time of order LA over 2, which maybe I'll show you, that means that the reduced density matrix is the same as the reduced density matrix we would get from a Gibbs ensemble. So the entanglement entropy must be the same as we would get from a Gibbs ensemble, and that's the same as the thermodynamic entropy, which is proportional to the volume of the region A, times basically the entropy density has to go like 1 over beta, the temperature, inverse temperature to the power d minus 1, and basically this sigma is the Stefan-Boltzmann constant, or it would be if we were talking about photons. Okay. So now we want to understand what happens for small t. Okay, so now, for example, I've considered the case where A is the interior of a sphere is a ball, right? But it doesn't have to be. It could be any compact region. It doesn't even have to be compact. B is the rest. At large t, when t is much larger than the size of A, as I just said, the entanglement entropy is going to go like the volume of A, and at t equals 0, we get an area law. So this thick line is the area between A and B. If we can show that for small t, basically this entanglement entropy grows linearly with t, if we can show that, then we expect it also to be proportional to the area of the boundary, as long as t is much, much less than the size of the system. So if this holds true, then the question is, what is v? Working in units where the speed of light is 1. Okay, and in 1 plus 1 dimensions, Pasquale and I showed that in fact v is 1 in our original paper, and once again this can be explained within the quasi-particle picture. This figure, which I spent a long time drawing about 10 years ago, has been copied and copied in various papers. It's been stolen. That's the problem. Anyway, so that's all right. I don't mind. I don't have a copyright on it, as far as I know. Anyway, so basically, for small time, the idea is that the entanglement between A and the complement B is due to the EPR pairs of which the one particle impacts on A, the other impacts on B. And you can see for small t, then the number of such EPR pairs is going to grow linearly in t until it saturates, when it's going to be proportional to L. So here's an example of a particle which entangles A and B, a particle pair. One strange thing, and so the entanglement entropy is constant, but one really bizarre feature of the quasi-particle picture, which is why it probably doesn't always work, is that for large t, if you ask where is this, what part of region B is this small region here, A, entangled with what part of B is it entangled? It moves further and further away with t. So at late times, this system thermalizes because it's entangled with the Andromeda nebula. So it's a little bit strange, to say the least. Anyway, that's the picture, and we would like to see how far we can actually push this. So now I'm going to talk about what we can do for entanglement spreading for d larger than 2. So there are rather few results, but a number of groups are actually interested in it. So there is this intriguing holographic result from Liu and Su, where they have an explicit formula for how nu depends upon d, but it's a very strange looking formula. It looks like d minus 1 to the power d minus 1 and various other things, right? So it's very interesting. So I'm not saying it's wrong. I believe I understand their arguments. Anyway, for 2 dimensions, we get the previous result of 1, and as you increase d, v goes downwards all the way to infinity, where it's a half. That's the holographic answer. Okay, so, and then Cassini et al. Recently just generalized the quasi-particle pictures, said really to higher dimensions, just said what I basically said, but that basically said that the entanglement is due to EPR pairs, but had some nice argument for what would happen if the pair, because in higher dimensions they don't just have to move in opposite directions, they can be almost collinear, for example. And the entanglement pattern that you get will then depend on how the entanglement between these pairs depends upon the angle between them. So they made various assumptions as to how that depends, and they got then various answers for V, but they actually proved an upper bound which is actually smaller than the holographic value, which means that the quasi-particle picture has to break down for holographic theories. And we have other reasons for why that is probably true too. But anyway, so it would be nice to do an ab initio calculation even just for a free field theory, and that's what I'm going to give you preliminary arguments for. Okay, so now we're just going to talk about free field theory. And we're going to start from, once again, this special state where now D is the Dirichlet boundary condition state. So, okay? So the nice thing about a free field theory, if you start from a state like this, evolve with a Hamiltonian, which is a free field theory, the state at any time t has to be a Gaussian state. So therefore, if you know the covariance of this Gaussian, the correlation function, you know the wave functional, right? So it's going to be e to the minus quarter times phi g inverse phi, such that when you square this and work out the expectation value of phi times phi, if you work out the variance, then you get g, okay? And it's useful to actually write this in another basis, which is the conjugate basis to phi. So basically, psi, if phi was an electrostatic potential, psi would be like a charge, okay? So this is just the Fourier transform here, but the nice thing is in that Fourier transform, you get G rather than G inverse, which is a nicer object to actually deal with. You might think this G inverse is simple. Well, G inverse in the d-dimensional space is very simple. It's the propagator. But this is G inverse on a space-like section, which is a non-local object. Okay. So we basically have that form, and then we can actually, okay, so we need to know the correlation function. And once again, we need to know this because we've chosen this particular state. We need to know it in this slab with the continue to real time, with the coordinate tau continue to real time. And the nice thing about 3+1 dimensions, so here I'm just going to now be talking about 3+1 dimensions. Odd dimensions are nasty in general. Even dimensions are nice. And there's a good reason for that, which you will see soon enough. Anyway, there's a really nice explicit formula that I like very much. I haven't seen this in the literature, but here it is. Okay, so basically, if you just look at the first term, it's independent of t, and in fact, this is precisely the answer that you get for the thermal correlation function of a free field in 3+1 dimensions. Okay, and then you get these corrections, and you see what happens for once r gets bigger than 2t, well it always is here, then this thing roughly becomes 1, but it cancels. These two terms cancel this term. So what you actually get is you get the thermal result up to a distance 2t, and then it's cut off exponentially. Okay, so this is precisely this light cone horizon effect, that when the 2 points fall within the light cone, the correlation function is exactly the thermal correlation function. And because it's a Gaussian theory, the correlation function determines the reduced density matrix. and therefore the system thermalizes exactly once the region falls within this horizon. There's a weird thing about free field theory in that if you take a massless free field theory, even at finite temperature, the correlations don't decay exponentially, they decay like 1 over r, whilst in an interacting theory you expect a thermal correlation length to get generated. So maybe this is a bad example, but it's the only example I can do. Okay, now the other interesting thing is, okay, so basically what happens is that for r bigger than beta, this is basically going like 1 over r, yeah.
Can I ask quickly, I mean, I might have thought that if you had a compactified free field, that would change. This is specifically like a non-compact boson.
Yeah, it's a non-compact boson, and
Can you do a compact boson?
in higher dimensions,
Okay.
yeah.
Well, I mean, because then you,
I think in high dimensions, a non-compact boson and uncompact,
it won't matter.
I don't think it matters, yeah.
So
I'd have to think about that, yeah. Yeah, it's a good idea though, yeah. Okay, so basically this is falling off like 1 over r, except at very short distances of order beta. And then so a very good approximation for the Green's function is this delta function at short distances, the 1 over r fall off here, cut off by this theta function, okay? Okay, and the beautiful thing about this thing is that it can be written as a convolution of the Green's function, of two Green's functions, of two retarded Green's function of the wave equation. That is, this expression here, including the theta function, can be written as an integral over x of a Green's function, a time-dependent Green's function. Okay, so this is precisely the quasi-particle picture, right? So basically, the correlation function here between x and x prime at time t is due to the emission of a pair of quasi-particles at time t equals 0 from a point x. This is a Green's function, integrated over all x. All right? And the nice thing about being in 3 plus 1 dimensions is the Green's function for the wave equation is concentrated on the light cone. So these quasi-particles move only along the light cone, and in odd dimensions this is not true. Okay, odd number of space-time dimensions, this is not true, and that's responsible for the failure of Huygens principle, for example, in odd dimensions. Okay, anyway, it works in 3 plus 1, and it works in 1 plus 1, it works in 3 plus 1, doesn't necessarily work in 2 plus 1. Anyway, I'm going to stay in 3 plus 1 and try to. So we can then use this to sort of massage the result for the wave function into this really elegant form. That is, we can write it as an integral over these fields at time t equals 0, which are the sources of the quasi-particles, okay, with a Gaussian weight times phi times the Green's function convoluted with phi. So this is a superposition over all phi's of a Gaussian wave function, and at each point in phi, it's a Gaussian centered around the averages over the phi's on a sphere of radius t. Okay, so what this thing does is average the phi's over a sphere of radius t centered on this particular point r, and that's what this expression is actually showing here. So this is a nice expression for the wave function, and from here we should be able to calculate the entanglement. It's better if we do it in this Fourier transform basis with respect to phi. So in the psi basis, then you can write it like this, and you have to kind of stare at this, but it's an integral over all space, integral over all space, psi at a point x times the convolution here. So basically, if we think about a simple geometry where A is everything to the left and B is everything to the right, then basically this thing can, phi can, because G only has a range T, phi can only couple to psi over a range T. Okay, so basically you can split this integral if C, so here's the boundary between A and B. If C is a region of width 2t about this boundary, this expanding region, we can break this integral over phi into an integral over just the phi's within C, and these are the only phi's that may entangle A and B. Okay, because anything out here can't reach A, and anything out here can't reach B. Okay, so the entanglement is only due to phi's within this region here, so we can actually write this like this, formally, but with explicit expressions here and here. And this is just the form of a Schmidt decomposition of the wave function. And you see, so what you usually call just a sum over n, which for finite dimensional Hilbert space is a sum, finite sum here, it's some integral over all the phi's within this region. But if you think about the log of the rank, it's the volume basically of these possible spaces. So if T is small, the rank of this Schmidt decomposition, or the log of the rank, is basically going to be the volume of C, which is increasing linearly in T. So what they call the n equals 0 Renyi entropy is increasing linearly in T. Until, of course, C completely overwhelms A. So if A is much smaller than B, then basically all of this part of C is going to be within A, and then it's going to go like the volume of A, and it's going to give us a volume law, which is what we expect. Okay, so you can actually push this, and the answer, I believe, though, this is a preliminary slide. I want to stress this. This is what I think happens. So this is the answer, I believe. So, okay, I've got a couple of minutes. So now, this is a two-dimensional picture, but remember we're really in 3 dimensions, okay? But I can't represent this. So A is some compact region. B is the rest. What you do is you draw a sphere, center R, of radius T. So this is where a particular source sits, okay? And then basically it is entangling all the fields on the boundary of this sphere. But, okay, so the amount of, so this sphere here intersects A along here and intersects B along here. The contribution to the entanglement is the area, okay, so this is the surface of the sphere is 2-dimensional. A is 3-dimensional. This 2-dimensional surface intersects A on the 2-dimensional surface. We can talk about its area. We work out the area of that intersection, multiply it by the same thing with B, suitably rescale it with the time t, and then integrate over all r. We can integrate over r because the entanglement entropy is just additive in all these phi's. So when you do that calculation, obviously what happens if t is really, really big, then basically this is only going to happen if r is a long way. It's only going to intersect B. It's only going to intersect A if R is a distance of order t from A, right? And then it's going to be pretty much a flat plane, and we integrate over all these R's, and what we're then going to get is the volume of A. Okay. Now the other limit in which you can do it is when t is very, very small, and then you have very, very small spheres, and they only contribute to the entanglement if they intersect the boundary between A and B, so you get something proportional to the area law, except it's proportional to t because that's because each of these spheres can be in a position t, but it's not exactly t, and it's not exactly t because you can see that what can actually happen is that there are phi's in the phi's closer to the boundary do more entangling than the phi's out here. So a phi out here somewhere doesn't only entangles a small region in here somewhere with B. Okay, so you don't get the one-dimensional result. You get something smaller than the one-dimensional result. And I claim that when you do this calculation, you get a third for the speed. Okay, so just to summarize, if we look at overlaps, they typically, in any CFT, they decay with an initial Gaussian to a plateau value. For holographic theories, this is believed to persist up to large times. The integrable theories, we get all this interesting structure. For if we look at spreading, in two dimensions, the speed is 1. In three-dimensional free field theory, to be confirmed, nu v is a third. Now, that doesn't mean it's true for all the 3 plus 1 dimensional CFTs. I'm sure it probably depends on the particular CFT. I doubt if it's universal. In odd dimensions, it's not even obvious that the quasi-particle picture even works, because this Green's function that we used actually has support inside the light cone, so that remains to be investigated, whether it even gives anything like this in 2 plus 1 dimensions. Okay, I'll stop there. Thank you for your attention.
How does that speed of 1/3 compare to the holographic?
It's smaller.
And how about the Cassini and?
Well, this is a particular case of the Cassini et al. Result where the quasi-particles are uncorrelated, where the correlations are independent, rather, of the angle between them. Yeah. So yeah.
I'm just wondering, for the case of the rational CFT in the first part of the talk, did you look by any chance at the Fisher zeros for your partition function?
Well, these are the Fisher zeros. Okay, these points on the real axis are the Fisher zeros.
The ones that, I mean, all this.
Yeah, so they're dense on the real axis.
I see.
And so the interpretation of the Fisher zeros is probably not your interpretation. It's to do with revivals.
Mm-hmm. I see. Well, others interpreted them as singularities.
Well, the point is that the beta of a quantum theory, in e sub minus beta h, is really not the same as the temperature of a classical system, which are the classical Fisher zeros. So I don't think it's quite the same thing. I mean, the quantum analog of the Fisher zeros will be if you take a quantum Hamiltonian and as a function of the coupling constant g, and you work out trace e to the minus beta h at fixed beta, and work out the zeros as a function of g. I believe, anyway.
That's right.
Yeah.
That's the one question. What about preterminals?
Yeah, well, there's an interesting problem. So I don't know. Yes, I haven't worked on. Yes, for some reason, some people like fermions, some people like bosons. Yeah. And of course, in one dimension they're the same, but not in higher dimensions.
Next thing you say, John, again.